So the size of that particle is comparable to the microstructure of the materials. Okay, and so by doing that, we can define an effective viscosity at the microscopic level. And we've also discussed that in the dilute limit, you can write down a pair distribution function, and you can analyze these equations in great detail. From that, you can calculate the microviscosity. And we look at how for a passive system, right, as you increase the speed of the probe particle, that goes down. And for active systems, again, in this regime, we cannot tell them apart from passive ones, but in this small velocity regime, we can tell that as you increase the speed, the viscosity is going to go down further compared to the passive case. So that's what we talked about in the morning. So we can also examine the microstructure of the system using Brownian dynamic simulations. So here are a few videos that we can look at. So there are 3 videos. Okay, so as we move from the top to the bottom, what happens is the speed of the probe particle is going to increase. And we're doing the simulation in the frame of the probe particle, which means the probe is fixed, and all other particles have a drift velocity to the left. Okay, there's a change of frame. And the circle here that I'm showing, the red circle, so that's the contact radius. And okay, so as you start the simulation, you see in this case, the velocity of the probe is quite small. So you can see they're undergoing their random motion, but you don't see a significant difference in the density between the front and the back. So that's when the velocity is small. And in the middle, the velocity of the probe is higher. What you see is there's a weak structure that develops. So essentially, you can think about it this way. So you remember that, again, we're in the frame of the probe. So all particles, in addition to their swimming velocity, they're also going to get a constant velocity that's going to the left-hand side. Okay? And if you're a particle that comes in the front, you have to either go up or down. And as eventually you're going to be able to slide off into the box. So this is where essentially so that the particle escapes. Which one is that? Is the pole does it do? Yeah, no, not quite. The red circle is the contact circle. So that's the location where is the radius of the probe plus the radius of the active particles. So I'm not actually showing the probe. So the probe is slightly smaller than that.
Can you please see what occurs if there is nothing that's dot stuck there?
Sorry?
The blue dots are blue active particles.
The blue dots are the suspension particles. Yeah, they're active particles. And I'm not, so their size are not exactly reflected here. These are just reflecting their center position. So their size is not true to the particle shape here. Because again, this is the contact radius, right? So essentially, these blue dots are the center position of the active particles. They have a finite size, so is the probe particle. And as you increase the swim speed, what you see is this weak structure that develops. And if you further increase the speed of the probe particle, okay, in the frame of the probe now, they have a larger horizontal velocity. So you see this again, this triangular wake structure as the particles escape from the back of the probe. So the way to understand this is quite simple. So if you think about an active particle that's at the top, okay, or at the bottom, you have essentially 2 velocity component. The u1, that's the velocity of the probe because we're in the frame of the probe. So the particles all get a velocity in the horizontal direction. And if you want to think about particles either at the top or at the bottom, in order to get behind the particle, what's your best chance? In this case, your best chance is you're pointing downward, fully downward. Then in that case, your velocity, adding this up, you get a velocity in this direction, right? And the angle here, beta, would be the ratio between the velocity u1 and that of u2. And you can measure this angle that's precisely predicted by this relationship. And as you increase u1, what happens to the angle beta? Is it larger or smaller?
So I don't know.
All right. So I'm increasing U1 at speed of the probe. Then what happens to this ratio?
Well,
That's smaller, right? So then beta becomes smaller, and you can see that that's indeed the case, which means the smaller angle, which means the extent of the wake is longer. Okay, so that's interesting. And you can also look at, for example, the density distribution of these active particles. You can do that in two ways. One is if you solve the conservation equations, you will get that directly. That's the first column. Okay. The other thing you can do is you have done these BD simulations. So what you have to do is you have to make small bins throughout the system, and you just count the number of particles within each small cell that you've described. Okay, you can draw regular grids and count them. So then from that you can also get a density distribution. So this is how they look like in comparison. Again, when the speed of the probe is quite small, the density difference in the front and back is not as significant. As you increase the packet number, the density in the front, which is on the right-hand side, is going to be much higher because you're moving to the right? You are sweeping up particles in front, and in the back, there's an empty wake there. And the other thing that's interesting is as you increase the speed of the probe, the density in the front is high, but the region shrinks. So there's a sharp boundary layer where the density is quite high, and everywhere else is more or less at lower density. Okay. Any questions? Yep.
U1 is probe density.
U1 is the velocity of the probe.
I'm like, probe
Yep.
velocity. So
Yep.
is the velocity the same?
Velocity of,
The same because
we'll move to the frame of the probe, but physically that's the velocity of the probe, right? Yeah.
So I can that is why is the direction used? Wait,
Which direction?
you want it?
Because the probe is moving to the right. Okay. In the lab, right? Now you're sitting on the probe, so the particles have to move to the left. If you're sitting on the probe particle,
So but U2 is particle.
U2 is the swimming velocity.
What?
You mean one is usually pointing downward? So we're listening about the weight structure here, right? So the way to think about that is if you have a particle, say, at the top, if U2 is in the horizontal direction, you're not going to get into the back, right?
Okay.
So we want to think about how can particles get to the back of the probe? That's somewhere here. How do we do that? We have two velocity components. U1 is horizontal. So particles at the top here, they move this way. If U2 is also horizontal or pointing to the upward. So the wake essentially, the boundary of where you have particles and no particles is dictated by the particle that gets closest to the back of the probe. Then the question becomes, what is the best chance of getting there? What velocity, what orientation should we take? For a particle at the top, should be going downward, right? Because you want to get to the back of the probe. So that's essentially gives you the boundary of where the particles appear. And the ratio would be the angle here. Make sense? Other comments? Okay, that's good.
Okay.
Still the PF.
Yeah. So this is the probe. Okay, right? In the frame of the probe, this is stationary, right? Now you have active particles. Say an active particle here. Okay, at the top, somewhere here. And the contact radius is this one, right? So I'm just tracking the center position of the active particle. So that's this location. Make sense? And then here what happens is, because you're in the frame of the probe, then these active particles, they all have an additional velocity that's horizontal, right? And if you think about particles at this location, they're going to the left in any case because you have a velocity from that. But the wake structure here is dictated by how this particle can get into the back. How much further can you do that? If you are going in this way, if your swimming velocity is also going in this way, then you will just, move in that direction, okay? if your swim velocity is in this direction, then you're going in this direction, or the wall, right? You're getting further away from the probe, so you're not going to get into the back of the probe. So the best possibility is when your swim velocity is pointing in this direction, then you can get to the back of the probe, and that's how you get the angle.
So they make the probe particle pointing towards the probe, right?
Yep.
Otherwise, it appears to that is what the direction we watch the probe. And when I'm saying they can escape, you have one direction going up, but then
They will escape. That's correct. Yeah. Which means they're not getting into the back, right? Yeah. Yeah. That's fine. So they have all these states, but they're more likely, of course, to be pointing into the probe because of accumulation. Yeah. Other questions?
oh, in this slide, this the calculated what is that subject
The color on the right-hand side?
yeah.
So that's the density of the active particles in space. So here's a color map here. So that's number density.
Stuff.
Yeah. So if you look at these graphs here, the key feature is on the right-hand side of the red circle, the density is higher because particles are moving to the right. So in the front, you encounter the particles from the suspension, whereas in the back, you leave the empty region. So in the back, it's the void region there. Yeah. Other comments? Okay, good. So in the case we studied here, we're looking at hard spheres without considering the fact that as these particles move around, they're going to generate disturbance flow in the fluid. So let's now try to take into account what happens in that case. So here's a sketch of what's happening. So the gray particle, again, is a probe particle, okay? It's moving to the right-hand side. Now, as you encounter this active particle, say this is a pusher, and then the pusher, generates a flow field like this. So the probe is trying to go to the right, but what does the flow field do to the probe particle? Is it pushing it to the right or to the left? Who think it's to the left? To the right? So I have a probe particle that's moving to the right-hand side. It encounters this active particle, right? Now we're not considering the fact that these active particles, as they move in the fluid, they generate a flow. Okay, so the red sketch is the flow field that they generate. So the question is, what does this flow field do to the probe particle that's at this location?
It's not about it tries to reduce its speed towards this.
So it's trying to push it to the left, right? Because the flow is going to the left, which means it's impeding the motion of the probe. Because the probe is trying to go to the right.
Yeah.
Right?
Yeah.
So what happens to the viscosity if you're trying to actively prevent it from going to the place where you want to go? So you increase the viscosity, okay? Whereas for a puller, the flow is in this direction, right? With the reverse, the probe still has to go to the right, and the flow is dragging in the same direction. So which means in the context of microbiology, actually pullers have reduced viscosity, which is the opposite of what you see in the bulk rheology measurement. Okay, so this is a lesson on that length scale matter a lot. If you look at this kind of dynamics, at the microscopic level, pullers actually reduce the viscosity. At the large scales, it's opposite. Try to plot the trajectory of one particle. Questions? So yeah. I can look at it.
Oh.
See,
medium transition conductivity why are we saying that at micro there is the group and then bulk there is no group?
So the bulk rheology is you take a large sample of fluid, put it into a rheometer, and measure it. There's no probe. There's a large rheometer that you're using. Okay, that's how you do a macro rheological experiment, right?
So in the micro case, you use the birth to measure the.
That's right. That's right. So we go back to the previous slide here. So if you do regular rheological measurement, you're taking a macroscopic sample. Okay? If you're doing a microbiological experiment, you're literally embedding a small particle into the material, whether in our case it's a suspension of active particles or other materials.
But then maybe as in same question that came with Dustin earlier, it looks like at micro scale that when the probe is there, easy then detecting the
Yeah, you have hydrodynamic interactions. That's correct.
then how it's beneficial to do it and
How is it beneficial to
do the measurement at micro in that way
the hydrodynamic interactions are always present, regardless of whether it's macro scale or macro scale. It's just the result of the interaction is different, it is all. Hydrodynamic interactions are long-ranged, so it scales 1/r. So even if you're very far away, in principle, there are still interactions. Yeah, that's correct. That's the correct behavior, right? Yeah. It's not whether it's beneficial. This is what happens with the physics of the systems. That's a reality, okay? Other comments?
So
Yeah.
this using this first step, we can mathematically find the viscous, what's this acid with this particle. So it's using this microscope doing the measurements.
You good? Yeah.
So and is that the purpose of going?
Yeah.
And you said what we have is
Yeah. And the purpose is about, like, I talk about the behavior within a cell, right? So if you want to understand the transport processes, for example, happening within a cell, within the cytoplasm of the cell, this is the only thing you can do. You can't do macrobiology because you're taking a big tissue rather than a single cell that you're looking at. So that's a wrong experiment to do, right? If you want to actually examine what's happening at the microscopic level, this is what you have to do.
What I want to say,
Yeah.
there's no apparatus as such. We have seen blend theoretically.
There is macrobiology is a real experiment that you can do. But, yeah.
I was saying like here's the new beta which we use, but there are also we can use some microscopic mirrors.
Yeah.
And we use just like to prove like this and
Yeah, that's it. The equivalent is trivial. Just put a particle in the media. Apply a force sound. That is it.
it's even a try to mimic that
Mimic which one?
mimic those
So then the theory we're doing is exactly modern rheology. That's exactly what it's doing. Okay? Yeah.
so well jamming like super noise plus well called you really also dimension.
Yeah. Bacteria.
So then this was a given piece.
Yeah. It's in the title here. Exactly. Yeah.
This thing that was causing.
Yeah. So yeah, exactly. So if you have bacteria in the fluid, it will reduce your viscosity. You're trying to go somewhere, but you have some bacteria in the water, and then it will push you around. Yeah. Basically, you can just imagine you're trying to go somewhere. There are little guys in the back. These bacteria are pushing you forward. Of course, it's easier for you, right? Then effectively, that means lower viscosity. Because I'm pushing. Somebody's pushing me. Okay. So that's essentially what's happening here. Other comments? Okay, so here we looked at the effect of the flow generated by the swimmers, okay? But there's, again, another aspect to this, which is the probe particle is moving in the fluid. The probe also generates its own disturbance flow, right, as it moves around. So that's going to, again, influence the dynamics of the systems. So we can consider that as well. So here's including the disturbance of the probe. Again, we're in the frame of the probe, okay? Which means then far away, there's a velocity, a homogeneous velocity. And you can solve the Stokes equations to figure out the flow field. So here is the string lines of the flow. The color is the angular velocity of the flow. Okay, the sign is different. At the top is positive, at the bottom is negative, but it's symmetric, except the sign. So that's the flow field generated by the probe moving in the fluid. Okay, make sense? Any questions about this? Because the probe generates a flow in the fluid, and the swimmer also there. They are going to feel the flow, right? They will be influenced by this flow. So if we bring back our plot here by looking at the viscosity as a function of the speed of the probe, we have seen these ones. One is the passive one. These are without considering the disturbance flows, just hard particles. So that's the passive, and that's the active. Okay, that's what we've seen before. If you include the disturbance flow generated by the probe, even for a passive system, you see that in this context, the micro viscosity is quite small now. And the reason is the following. So if you consider a passive particle, okay, not swimming, passive. But this passive particle is in this flow field. What happens to the particle? It goes with the flow. So it moves to the back, which means if you look at the previous graph, where as the probe is going to the right, the density here is higher, right? But in the presence of the disturbance flow, particles are going to migrate more to the back. So that will reduce the density difference, and you will reduce the viscosity. Okay, that's for a passive system. Now, for an active system, it's further reduced, and it's now negative in this particular case. Again, when the speed of the probe is quite high, there can be a difference between active and passive. So the black and the green are the same. Okay.
So what does what happen for making it?
I'll talk about that in the next slide. It means that you normally positive viscosity, you apply force to the right, then you go to the right. Now, if you want to move to the right with a constant velocity, you have to apply force in the back, because there are guys in the back that are pushing you forward. Okay, right? So in this case, if you think about an active particle, again, somewhere here, the flow is non-uniform. So it's going to rotate the guy, as we talked about in the upstream swimming case, right? So it rotates in this direction, and it's going to reorient these guys to the back of the probe. Now you have a velocity component that's pushing to the right-hand side, okay? That is pushing you forward, actually. So you don't have to apply as big external force. In this case, you have to actually apply a drag force, because otherwise you're going to accelerate. And we're doing this by taking the fact that the probe is moving at a steady velocity, okay? So that's mean in this measurement, it's negative, okay? Yeah.
This phenomenon can be small velocity larger velocity down to small velocity of the probe, small velocity of the probe. If the probe velocity is very high,
Much larger than the swing speed, as someone observing. Again, I can't tell whether there are active particles in there, because the probe speed is so high, it's not going to see the swimming motion, right?
okay, other comments?
Yep. So the signal for left hand side, which is basically signal, some kind of magnetic effect signal.
Sorry?
So magnetic effect signal, between signal like to magnetic like there is a ratio difference to which the ball straights are.
And it's just the fact that, so when you have a particle in the fluid, right? Particle is moving with some velocity. So at the interface between the particle and the fluid has to follow the particle motion. That's all. Because when no slip. In magnets of technology, like it is doing the three limits instead. The certain can CMI stored. If it is spinning too much, then the ratio will go ahead. It's not the same, but
Yeah. Yeah.
Obviously, whenever the air is spinning, then like it only spin that way. So it's just a low slip. Yeah, exactly. And the spinning here to the particles is because the flow is kind of uniform. So you have a gradient, shearing that's happening to the swimmers. Other comments?
Okay, so let's think about this in a bit more detail. So what we looked at, so you can operate microbiology at different modes of operation. The first one is you just apply a steady force to the probe, and then you look at how the particle moves, right? The one we looked at here is the other case, which is I set a constant velocity to the right, and I want to ask the question is how much force do I need to apply in order for that to happen? So the modes of operation is important for the context of active systems. So if you think about it in general now, you have a probe moving at a constant velocity, okay? In a medium, suppose for some reason that's negative, what's happening to the probe? What do you have to do in order to maintain this constant velocity? So I have a probe moving at a constant velocity in a medium with a negative viscosity. How do you make that possible? What kind of forces do you have to apply? Because remember, the net force has always to be zero. Force has to be balanced.
You apply force
To the left. Okay, so that's okay. That's fine. But you just apply a constant force to the particle. Okay, that's all you're doing, and then you watch the motion of the particle. If for some reason the viscosity is negative, what happens to the particle velocity?
Can you go that way? Probably would.
No. So in this case, I just have a constant force applied to the particle. That's all. Okay, and then the particle is going to move. It's going to,
With the right.
but it's going to accelerate, not just moving to the right. It's accelerating. Yeah. So your that accelerates right to the right. So when you accelerate, what happens? You change the Pecking number because you have a higher velocity. The Pecking number becomes large, right? So if you go back to this slide, if you accelerate and your Pecking number increases, then what happens then? Becomes positive. Okay? Which means if you do this experiment at steady state, meaning that when you look at it, when the particle velocity has stabilized, what are you going to measure? You're going to measure positive viscosity. Okay, so you're not going to get that. This only manifests in a transient, whereas in this case, if you artificially fix the velocity, you can see it at a steady state. So that's the difference between these two operations. Any questions? Okay. So let's think about this a little bit more. So if you have a negative viscosity, this is what we do, the constant velocity probe, right? You have to actually apply force in the opposite direction. So if you look at the average force, you can define a microscopic viscosity. Can you also quantify the variance of the force? And can you connect that to the fluctuations that's happening in the suspension? Okay, that's a question we want to think about. And actually, to do that, let's think about a simpler problem where we have a Brownian particle as passive, okay, in a harmonic fab. This is a potential energy. So in this classical problem, what is the distribution of the particle? It's Boltzmann, right? For a passive particle in a potential field. And so this model problem is nice because what you can do is if you look at the probe has a position relative to the center of the trap, okay, that's R, and the spring is exerting a force on the probe, okay? So both are fluctuating because you have Brownian motion going on. So the position is fluctuating, which means the force is fluctuating. The force is the spring constant times the position. So if you calculate the standard deviation of the force, trap force, and the standard deviation of the position, their product is a constant. Okay, this is an exact calculation, which you can do. The constant is the dimensionality times kVt. Okay, so that tells us something about this operation. So this operation is pathological in a sense that if you were to measure the variance of the force, you are going to get something, but that's not going to reflect what's happening in the suspension. The reason is the following. So what happens if you fix the kinematics of the particle? So you fix the velocity, which means the position of the particle is fixed artificially over time. Do you have a fluctuation in the position? You didn't allow it. Theoretically, you did not allow that, which means the fluctuation in the force blows up. So it's a pathological model trying to represent what's actually happening in the experiment, which means we want to relax that to take a model that's more realistic compared to what's happening in an experiment. So in an experiment, this is what's happening. In this example, for example, laser tracer microbiology, again, you have a particle, the gray particle, embedded into the material. I apply an external force on it, and the trap force, say, tries to move it to the right, but the particle is not going to exactly follow the center of the trap, okay? So there's always fluctuations allowed, delta x, between the position of the probe particle and the center of the trap, which is the force that you're applying. So that can be modeled exactly as the simple case where let's just put the probe on a trap force, okay? And we move the trap. So as the trap moves, the particle on average is following the trap, but it's allowed to fluctuate, okay? And that's a better representation, again, of an experimental equipment. Okay, any questions about this? Okay, so that's fine. So now we have a probe that's trapped by a trap, and then the trap is moving, potentially. So again, you can write down your Rheology equation. Here I'm writing that down for an n-particle system, so this doesn't have to be dilute. So now you have n suspension particles that could be active. Okay, again, we've seen this before, so you can write down the fluxes. In this case, each particle has its own translational flux and rotational flux. So that's written in this case as the total velocity that you get in each coordinate, as we discussed before. And you have potential hydrodynamic interactions among all particles. So your mobility matrix here, this is a large matrix, okay, including all n particles. And in each coordinate, you have your forces and torques that you can include. Okay, you can have external force, propulsive force, or force due to interactions among particles, and Brownian motion. So you can write down this equation. Of course, solving that is a separate story. You can write it down, you can analyze it. It gives you some interesting result. But let's not get into the mathematical details about that.
Say with the discussion, yes. I'm saying that this cannot be solved very good. Yes, because each particle has, say, 3 dimensions. Each particle has x, y, z, 3 positions. And if it's an active particle, each particle has 2 angles. So for a single particle, that's five dimensions. And you can solve a 5-dimensional PDE from geometry, because you're going to run out of numbers. Because you have to discuss the partial differential equations, right? If it's 5 dimensions, say, for example, in each dimension, let's take 100 ones. That's yeah, I haven't even talked about 8. Just talk about even 1. It's impossible. Because you don't have enough memory for it, right?
Yeah.
So if you have n, that's 5n degrees of freedom. Say n is 10, that's 50. So you can't solve the PD directly that way, right? Other comments?
Can we show a simple thing? So this is a so-called curse of dimensionality. You're solving PDEs. Can you do some, like, as opposed to like some flexibility?
Okay, so you want to analyze these equations in certain limits. Yeah, we can do that, definitely. And that gives you some nice structures that you can look at. Yes. Other comments? Okay. So let's think about that. So this gray particle, that's a probe particle, right? It's being trapped by an external force, and you're trying to drag it along. And you can define a trap boundary. Essentially, how strong is the trap force? Okay. And you can think about, again, we can make use of the relation we had before. Instead of measuring the fluctuation of the force, when you artificially didn't allow the position to fluctuate, in this case, you can do it now. So you have fluctuation in both the force due to the trap and the position that has dimensions of energy. So I can call that an energy of fluctuation, which this quantity now indeed does reflect what's happening in the suspension now, okay? So what happens when the trap is very strong, which means the force of the trap is much higher than, say, the swing force?
Cannot escape then.
They cannot escape. And what is this fluctuation that you're going to measure? So I'm still trying to measure this quantity here in the case where the trap is very strong. It's a very tight trap.
What happens to the swimmers? Can they that's the position of the particle.
How much force?
Yeah, that's a position. Doesn't go much. Yes, and the point is because the trap is very strong, you
So
can't
for the
really
second
swim.
exercise, you have to do your own
Right? So you don't get to manifest your swing diffusivity because you have to take a step. You can't take any step now. Field is very strong.
So what kind of fluctuations you're measuring?
Thousand.
The thermal energy or Brownian part. But that part doesn't, this trap cannot affect that part. So that's one limit. You're talking about asymptotic limits. That's one limit you can exactly calculate.
So if it was a passive case,
Passive,
like if say it's just a passive bar.
you mean these blue ones? Yeah, that's the same, right?
Also we will have
Yeah. But because the trap is so strong, you suppress activity.
the passive particles will not be affected by the
It's Brownian fluctuations. You can't, Brownian fluctuations are unbounded. And
acoustic.
yeah. There. That's a great point. Yeah. Other comments? Okay, so what if you have a weak trap, which means essentially the radius of the trap is quite further out compared to the position of the gray particle. So in that case, actually there's a separation of time scales. So you can look at the time scale it takes for the particle to get to the trap. Because the trap is quite weak, that time scale is large, right? Within that time scale, the particles has already explored the suspension because the trap again is far away. If you have explored the suspension and realize there are particles around you, what are you going to measure if you were to measure the mean square displacement? You're going to measure your effective diffusivity in the presence of other particles, okay? And that actually you can analyze the equations to figure out what that is. It has a very nice structure. So you have your own Brownian part because you've already explored the environment and the trap is quite far away. So it's much larger than your step length or your persistent length. So you have gone through random reorientations, okay? Then you will pick up the swim diffusivity. You have also discovered there are other particles near me, so you would have a pair interaction contribution to the diffusivity, okay? But eventually, you're going to reach the boundary of the trap and realize I'm not in free space. I'm actually trapped there. So once you cross over to that regime, again, you can measure this fluctuating energy, okay? And that's just given by, so previously it's the drag coefficient times the Brownian diffusivity. Now it is the drag coefficient times the diffusivity that you have realized before you reach the trap boundary. Okay, so that's for a very weak trap. So that's a very nice result. Physically, that makes sense because the trap is very, very far away. You have already undergone your random reorientations and collisions with particles. So what you're doing here at this time scale from the perspective of the trap is you're doing some effective random walk, and that diffusivity is coming from all these contributions.
Okay.
Yes.
You could.
Yeah, you could.
Yeah, you could. You
Yeah,
measurements. You realize.
Passive and active are different. Yeah, that's correct. Even in the case where you're measuring the viscosity, you can also distinguish them, right? Yeah. But the point here is to have a sensible measurement of what's going on in the suspension. Whereas if you artificially, so in this previous theoretical model, you've artificially didn't allow the position to fluctuate. You can still do a Brownian dynamic simulations of this system, right? You can measure the variance of the force. People have done that. And there's a puzzle is I measure this and I get nonsense out of it. And now the reason we know right now is because you can't artificially constrain the velocity.
Correct.
The trap is harmonic, yes. It doesn't have to be, just have to be soft, okay? To be soft, meaning that particles are allowed to deviate from the trap motion.
Trap moves.
You apply a force on it. Yeah. Or a potential, or just apply a force on it, that's fine. So long as it's flexible, and then you're okay. Because that's, after all, that's what's been happening in experiment, right?
Madam.
Other questions? Okay, so we've concluded our part on microbiology. So we're now going to move on to talk about the next topic, which is a mean field theory for active suspensions.
Yeah.
So let's consider we have a system, just active particles in water, okay? We want to develop a mean field theory, essentially a continuum theory describing the mechanics of this suspension. So here's a sketch. We have a volume, and there are a number of particles in this volume, okay? And we can write down a conservation law, again, for these particles, same as before, no difference. And the only thing new here is the interpretation of the velocity u. So now the velocity, what is this u here? It's not an external flow that you've applied. It is the mean field velocity that's been generated by all these particles themselves, okay? Similarly, the angular velocity that you get for a particle is from the disturbance flow generated by these particles. And
Good.
so I have a suspension, active particles in water, okay? Okay, in a volume. So if you consider the probability density of these particles, so the density in space would be integrating out the orientational degree of freedom, okay? And we're going to do this in the sort of dilute regime. Now, when you think about hydrodynamics, their interaction is long-ranged. Even if it's fairly dilute, you would still have interactions among particles. And we'll talk about the reason of that in just a moment. But for now, let's consider normalization of the density properly.
Okay, so on the right side and side you have this density function.
Yeah.
Any function of position, orientation, and that.
Yeah, so that's the full. Yeah, so that's the full over the angle to get the density in physical space.
Right.
And
You do we do that in the last years?
we've done this all the time to equate all the rotations to get the density in space. Yeah, that's the same operation we're doing here. Right?
So you got to change everything over on that part.
Yeah, and then I just care about the density for now because we're going to have further normalization because we're now dealing with actual, mean field modeling. So if I integrate the density in space, dv or dx, what do I get? I get the total number of particles in this volume, right? Over volume v, I get n. So that's the definition of a number density, okay? So let's define our system density, or a bulk density. Let's call that n infinity. That would be the total number divided by the total volume. So that's n over v. Okay? Which means, let me rewrite this. So I have n dv. N is the integral of p x q t dq. Okay, and then there's a volume integral. So that is n. Okay, so if I divide both sides by 1 over v, that's n over v, right? That's the system density. Okay, I haven't done anything yet, just finding the normalization. Okay, that's fine. And then we write down our conservation law for the probability. As we've done before. So we have two flux vectors. One is in position space. So in this case, again, we have three contributions. One is these particles are swimming. Second, there's a flow field, which we'll talk about in a moment. So the flow here is self-generated by these particles. Diffusion. And we have a rotational part. It's angular velocity due to the flow and the Brownian rotational diffusion. Okay, that's not different from before in terms of the equations. So now we want to think about how are these flows generated by these particles. Okay, so we talked about pushers and pullers. So let's model these guys. So for a pusher, the flow field, if you think about an E. coli bacteria, okay, so the force it exerts onto the fluid is in the following form, right? Something like this. So if you zoom out, you see again a force dipole. Right? So now, because we're looking at the system in a fairly dilute level, so if we have these force dipoles, so in the context of the flow, then we just have a distribution of force dipoles in a fluid, in the medium. Okay, for example, you have one here, somewhere here, another one in a different direction. If we know the disturbance field generated by this force dipole and this one, so on and so forth, we can then add them up to get the net velocity we're getting in a fluid. Sorry? Yeah, you have more than one particles in the system. So we need to add up the disturbance flows that each particle is generating. If it, no, unless you have a particle that's generating exactly the opposite flow of this one, you can cancel on the flow. It is possible there is that state, but that's not always the case, depending on the distribution of particles, right? Okay?
If it's very dilute, then there's a chance that it's not actually randomly oriented. I mean, if it was not dilute, it had a lot of factors. And then even because of random orientation, you could have cancelled each other out.
You could have that state, but it's not always there. It's a possible state that the system are in, but it's not the only state that you have, right? Other comments? Okay. So if we have, so let's define the following quantity. So let U D x minus x naught q. So let's define this field, velocity field. So that's the velocity field generated by a particle, by a swimmer at location x naught. Okay, the swimmer also has an orientation q. Okay, so here's a sketch. I have a swimmer here, okay, in the direction q. So its position relative to a lab frame of reference is x naught. Okay, and this ud, written in this way, is looking at the velocity that I'm getting at another location x. Okay, so this is ud x minus x naught q. Okay, that's the flow generated by the particle at position x naught, and that's present everywhere in the fluid. Okay, any questions about this? Of course, we haven't talked about how do we calculate this ud. We'll do that later on. For now, let's just think about this notation here, that we have this flow we will get from somewhere else. And if we have that, and we have another thing, which is the density distribution of the or probability distribution of the particles in space. And yeah, question?
Well, it's not understood. What is X?
X is a field point in the fluid, anywhere.
Yeah.
Right.
So that is X is our point of interest.
X is any arbitrary point in the fluid.
And
X naught is the position of one of the part of the swimmer.
So what were we seeing at X?
You're saying a flow. So this guy is moving around, so it generates a flow in the fluid, right?
So we are saying that the cross is the origin. Like it's a frame of reference.
What is crossing the origin? That's a reference frame to define X and X naught.
That is the frame of reference.
Yeah.
Reference.
Yeah.
From there, X naught vector is the position of the swimmer.
Yes, correct.
Which gives a kind of flow which we see X from.
You see you're observing. You can observe the flow at any point X, which is arbitrary.
The charged particle giving a flow.
Yeah, it's the same thing. The field is everywhere. Flow is everywhere, generated by this swimmer at location x naught, with a particular angle, particular orientation q, right? So that's the definition. So this is present in the entire system. And we also have the distribution of these swimmers in space, right? From our probability density function. Then we can get a mean field velocity. We just add these up, weighted by the probability distribution. Okay? So the mean field flow would just be at a position x, I say at a particular time, is I'm going to integrate over the volume and integrate over the orientations of the particles, just add up the flow generated by each of these guys with a particular orientation, okay, weighted by the probability distribution at x naught. Okay, so this is x naught, q, t, and this is dq, and over the volume. Right, so I'm adding up all the flows generated by each of these guys, and that gives me the mean field fluid velocity at a particular field point at a particular time. Any questions about this? Okay, that's great. So now the question is, let's calculate the flow due to a single swimmer.
So we are considering UD is the for one of the particles, right?
Yeah.
So we are averaging it over the whole probability density to get a mean of this UD, right?
Exactly.
That is how we are calling this the mean field.
Yeah, so you have a lot of swimmers in the system. You have a defined density distribution. Each swimmer contributes a UD that's specific to that swimmer. And you add them up. You don't just add them up simply, you add them up weighted by their probability density. Right? That's the definition of a mean field flow or any quantity. Other comments?
So can you go back about when you started the mean field theory of active suspension?
So previous Here
Yes,
I haven't done
Okay, so
anything.
yes, I
Yeah.
get it, yes.
Here, of course, I have the flow here already, but point is we don't know what that is.
So obviously the probability density is like a function of x1 because that's what the swimmer is.
Which one is?
So,
In the averaging?
yes, yes.
Yeah, so that's where the
Swimmer.
swimmer is. And
And that's why the swimmer's influence is felt.
and here you have to actually let me write this more precisely. Here the interval is over the position of the swimmer. Okay? Okay. Not so x is a field point we're looking at. Sorry?
It's not is the
Yeah, that's the position of the swimmer. Yeah.
It's different for different things.
It's different. Yeah. So that's reflected in the distribution here. P as a function of x naught. Yeah. Great. Thanks for catching that. Any other comments? Okay, so we're right on time. Let's take a break before we come back.